Hello now. Well, we're moving into chapter 7, and we're going to get pretty deep now into the idea of integration and what's called a differential equation. A differential equation is an equation that involves a derivative. So here's an example of of what a differential equation looks like. dy dx equals usually just something in terms of x. And what we're trying to do is solve for y. In other words, find the equation for y, find the expression for y such that dy dx is equal to f of x. So let's just look at a simple example. Suppose I tell you that dy dx is equal to e to the x minus x cubed plus sec squared of x. What does y equal? Well, we basically are integrating here. So y will be e to the x minus 1/4 x to the 4th plus tan of x, right? And don't forget the fact that there can be a constant tagged on here. So one step further, an initial value problem, IVP, is simply a differential equation with an initial condition. And the benefit of the initial condition is that it allows us to figure out what that constant is, what that value of c is. So here's a real simple example again. Suppose you were told that dy dx is equal to e to the x minus 5, and it contains the point 0, 2. In other words, the function whose derivative is e to the x minus 5 contains the point 0, 2. Well, again, simply integrating here, we get e to the x minus 5x plus a constant. And now we use our initial condition. 2 is equal to e to the 0 minus 5 times 0 plus a constant, and that implies that this constant is equal to 1, correct? So therefore our solution is y is equal to e to the x minus 5x plus 1. So just to make sure you understand what we're saying here, this function satisfies the condition that its derivative is e to the x minus 5, and that this function contains the point 0, 2. So that's an example of an IVP. Okay, let's take a look at this problem. It's a little bit more interesting. One of the things we want to point out right away is that there is no function whose derivative is e to the minus x squared. We say that e to the minus x squared is not integrable, but we still have a way to get around this. And our initial condition is that when x is 7, y is 3. And here's the cool way that we have of approaching this problem. What we do is we can simply say, without really any calculus at all, that y is equal to the integral from 7 to x of e to the minus t squared dt plus 3. Now let's take a look at this and make sure we see why this works. We know from the fundamental theorem of calculus that if we take the derivative of this expression with respect to x, we get e to the minus x squared. And we take take the derivative of that with respect to x, we get 0. Furthermore, if x is 7, if I put 7 in for x, and I integrate from 7 to 7, this whole thing will be 0, and I'm left with 3, which is exactly what I wanted. So that's kind of clever, and it's a good example to see because it does pop up from time to time. Okay, let's move ahead and talk about slope fields, which is another way that we can look at the whole idea of a derivative and a differential equation. And what I'll try to do here is bring in a computer-generated slope field and talk about it a little bit. So for our first example, we're looking at a slope field. Looks kind of cool, doesn't it? For the derivative dy dx equals cos of x. So think for a second, what function do we know whose derivative is cos x? Well, one of them is sine x. And if you look right here and I follow these along, that looks like it's going to be sine of x. But we also know that, sine of x plus 3 is a function whose derivative is cos x. And so over here we see sine of x plus 3, or sine of x minus 5. So essentially, here's what we're saying is that if this point right here, say, we're on the graph whose derivative is cos x, then its tangent line, or its derivative, would look something like that at that point. So we'll just keep moving along, and hopefully you'll get the idea of this. Alrighty, so this is a little bit more interesting one, and here we have a differential equation, dy dx equals x plus y. And you'll learn soon enough that that's not something that we can easily solve. And so we have to look at this slope field and get an idea of what's happening. Over here, as we move into the first quadrant, x and y are both getting bigger, and so our derivatives are very, very positive. Right along this line, you see that that's pretty much where it's negative, and that means that the sum of x plus y is going to be negative. More interestingly, look right along this line here. That's the same as the equation y equals minus x, and notice that in each of those places the derivative is 0. Over here in the fourth quadrant, both x and y are negative, and when you add two negatives together, it's going to be an even greater negative, so that's a very negative slope there. So, the way this works with an initial condition is we're told something like, okay, suppose the graph goes through this point, and we kind of just trace it along, and it might look something like that. But the next slide will help you see how the computer can really help us generate a slope field, especially when it has an initial condition. So this picture might be the most helpful. Here what we're given is the same exact differential equation, and we're given an initial condition that when x is 2, y is 0. Notice that that point is right there. So what we do is we start from that point and we just kind of move along, and we notice that as we move along and we're pointing ahead, this gets steeper and steeper. When we go backwards, it looks like it gets pretty flat. So you'll learn techniques for solving this differential equation with an initial condition that will be used on the calculator. But for right now, let's just say that it looks like on the right side of this, the graph is very exponential, and on the left side, the graph seems to be pretty linear. So maybe at the end of this lecture, I'll show you how we do this on the calculator. So now let's look at Euler's method, another way to approach the solution of an IVP. And it's a very tabular method, very arithmetic, but it's an interesting way to show you how to generate basically a table of values given an IVP. So here's our problem once again, same problem as before, same IVP as before. And what we're going to do is use a step in the x direction of 0.5 to approximate y of 2. And in so doing, we're going to generate a table of values. So I'll set up the table and then talk you through it. Okay, so take a look at this table. Here are my x's and here are my y's. Here is the derivative at any x, y. And remember the differential? This is saying that the change in y along a tangent line is equal to the slope of the tangent line times the change in x. And let's just remind ourselves that this change in x, we're going to use 0.5 here. You should believe that the smaller choice that we make for dx, the better our approximation is going to be. So here's how we do this. Here's how we get an idea for an approximation for y of 2. We start with the point that we're given, which is when x is 0, y is 2. So for those 2 points, f prime of x is 2, and dy is equal to 2 times a half, or 1. Okay? So now my next x, I'm going to increment it by a half, so it's going to be 0.5. My dy is 1, and so my new y is 3. My derivative is x plus y, so that's going to give me 3.5. And now dy is 3.5 times a half, or 1.75. Get the hang of it? I increment x by a half, and so now it's 1.0. My new value for y is the old value of y, which was 3, plus the change in y, which is 1.75. So my new value for y is 4.75. I add those two numbers together, and I get 5.75 for the derivative. And so dy is that times a half, which is 2.875. My new value of x is 1.5. And now what I do is I add my old value of y with the change, and I get my new value of y, which is 8.625. I add those together and I get, isn't this fun, 10.125. That's why this table just keeps everything so well organized. And now finally I'm where I want to be, which is 2.0. And so my final answer now for my value for y is, see if I get it right. Let me just take for a second. Just had to check my work. So my new value for y at 2.0 is 13.6875. And that's an approximation for y of 2. And that's how Euler's method works. It's kind of cool, but truly with today's technology, it's a little bit old-fashioned. Okay, so although it's a little small, hopefully you can read the URL, the direction. That'll bring you to the Inspire manual on the NMH Math webpage. And this is a manual that the math teachers have created, and it's specifically for using the Inspire in high school mathematics. So it's a good resource, and if you haven't seen it yet, you should. So what we want to just do here, I'll just give you a quick little screenshot of how you can use the Inspire to solve both a differential equation and an IVP. So what you see here is the command that'll give you the solution. And it's a general solution, that's why this constant is here. And so just to make sure you follow how this works, y prime, the derivative, is equal to x plus y. My independent variable and dependent variable follow. Now the IVP is the same statement, except it says and y of 0 is equal to 2. And when we do that, here is what we get as our solution. Now just notice this. When x gets very big, this term dominates and the graph is very exponential. And we did notice that on the slope field. When x gets very negative, this term goes to 0. And basically what we get is minus x minus 1. And if you remember, the left side of that graph was linear. And so this all makes sense as a possible solution. And I'll just point out again, we will have techniques algebraic techniques for solving IVPs, but the particular IVP, which is dy dx equals x plus y, we will not consider how to solve that in the scope of this course. All right, so there we go. See you next time.